Welcome back, AP Statistics. This is part 2 of chapter 13. We're going to be talking about the formal rules of probability as well as some applications of those rules. Rule number 1. The probability of an event, let's call it E, is some number between 0 and 1, and that is inclusive. The probability of the event is 0 means that the event cannot occur, and probability of the event is 1 means that the event will always occur. Rule number 2. The set of all possible outcomes of a trial has a probability of 1. What does that mean? In other words, if the probabilities of each individual outcome were all added up, their sum would be 1. In other words, something is bound to happen. This is called the probability assignment rule. That means that when the sum of the probabilities is in fact equal to 1, that's a good thing, and we should have a term for that. We would say the assignment of the probabilities is legitimate. Rule number 3, the probability that an event does not occur, or the probability of the complement of the event, is 1 minus the probability of the event occurring. We use this notation right here. The probability of E with this little exponent like C, although that's not an exponent, it's a superscript that just means the complement of the event. So the probability of the complement of the event, we could understand that as the opposite of the event, is 1 minus the probability of the event. In other words, the probability that an event doesn't happen is 1 minus the probability that the event does happen. And this is referred to as the complement rule. So for example, the probability of not rolling a 6 is 1 minus the probability that you do roll a 6. And just to be clear, 1 is the same as 100%. Now let's get into some more interesting rules of probability. Rule number 4, provided that two events A and B are what we call disjoint, another phrase that you might hear that means the same thing, is mutually exclusive, meaning that they have no outcomes in common, that is, that events cannot occur at the same time. The probability of A, what is that? Well, that means or. Probability of A or B, meaning that if either A happens or B happens, the event as a whole is satisfied. The probability of A or B happening is equal to the probability of A plus the probability of B. Here we can see a picture of what disjoint sets would look like. And here are events that are not disjoint. There is a bit in the middle that overlaps, and we would refer to that as the place where A intersects with B, all right? So just like this means or the technical term is union, this right here denotes an intersection of sets, which we see in the image right here. Again, we note that this symbol here, union, means or, as in if either A or B is satisfied, the event A union or A or B would be satisfied. And this is called the addition rule. So let's apply our addition rule. When we get to the light of College and Main, it's either red, green, or yellow. Of course, it's a traffic light. We know that the probability of green is equal to 35%. That's from a prior problem. So suppose we find out the probability of yellow is about 0.04. What is the probability that the light is red? Think about how we can use the concept of disjoint events and the addition rule to solve this problem. Pause the video, give it a go, and check your answer against mine. All right, let's look at the answer. So if we want to find the probability of red, we can use the complement of the event. Well, what's the complement of red? Well, that's going to be either green or yellow. So 1 minus the probability of green or yellow is going to be the same as the probability of red. So green or yellow. Are they disjoint events? Well, I would say absolutely. Light can't be green and yellow at the same time. So we'd say 1 minus, well, we simply add the probabilities here to find the probability of green or yellow. The complement of that would be how we find the probability of red. So 1 minus this sum here would be 0.61. Now let's learn some more formal rules of probability. Rule number 5. Provided that two events A and B are independent, meaning that the occurrence of A doesn't affect the probability that B occurs, we would say the probability of A intersect B, or A and B for short, would be equal to the probability of A times the probability of B. All right, so this is kind of like the addition rule, except instead of saying the probability that A or B occurs and the event is fulfilled, A and B both need to occur for the event to be fulfilled. And in that case, we would use multiplication. So we note that this means and. The technical word is intersect, but most of the time we just say and. As in, probability of A and B is satisfied only when both A and B occur in the context of one trial. And this is called the multiplication rule. So just like we had an addition rule for an or statement, we have a multiplication rule for an and statement. Specifically, this multiplication rule applies when A happening does not affect the likelihood that B happens. If there is some kind of a link, if the occurrence of A does affect the probability that B occurs, and vice versa, we would need a slightly more complicated formula we'll talk about in a little bit. Now we need to talk a little bit about independence. I've said before that independence is one of the two most important terms in statistics, the other being significance, in my humble opinion. So that we can often assume independence of events, especially when we rely on randomization or other sound stats methods, sometimes it is actually challenging to determine whether or not events are truly independent. So we can assume that if 10 movie critics, for example, are randomly selected and interviewed separately, we can estimate the probability that the critics like a film. All right, so those are independent reviews. One review does not affect another. However, if we gather 10 movie critics in a room and ask them how they felt about a movie, perhaps the notes that some critics give would influence others' views of the movie, as it were. We cannot assume independence here because it would be foolish to think that some critics voicing their opinions, especially critics who have been in the movie critique game a little longer, it'd be foolish to think that's not going to have an influence on other movie critics. So we need to be careful about when we assume independence. But a lot of the time, we're going to conclude that we can assume independence. And this will be one of those examples. We've determined that the probability we encounter a green light at the corner of College and Main is 0.35, a yellow light is 0.04, and a red light is 0.61. And we're going to think about our morning commute in the week ahead. All right, so the rest of the problems related to this section are going to be about moving through this intersection and what light we're going to see. Okay, so here we go. What is the probability that you find the light red both Monday and Tuesday? So we encounter a red light on Monday and a red light on Tuesday. Think about how you would do this. Think about whether getting a red light on Monday at all affects the odds of getting a red light on Tuesday, and see if you can come up with an answer, and then check it against mine when you're done. Okay, I'll assume we're ready to continue. So the probability of red and red is going to be 0.61 times 0.61. That's because red on Monday and red on Tuesday are independent events. landing at a red light on Monday does not affect the odds of landing at a red light on Tuesday, at least not that we are aware. So we would say 0.61 times 0.61, and we would get a 0.372. So that would be the probability of reds on Monday and Tuesday. Now here's an even more interesting problem, same scenario as before, but different question. What's the probability you don't encounter a red light until Wednesday? This one's a little tricky. Think about how you would set this up using independence and the multiplication rule. Pause the video, give it a go, and check your answer against mine. Okay, I'll assume you're ready to continue. So we want to find the probability of the complement of red, so not getting red, and not getting red, and getting red, okay? So it's not just that we don't get red twice, we need to, yes, get red on the third occasion, okay? Because we don't want to encounter a red light until Wednesday, but we do want to encounter a red light on Wednesday. So we need to factor that in. Literally, it's going to be one of our factors. So we have the complement of getting a red light and the complement of getting a red light and the getting the red light on Wednesday. We multiply all that out, we get almost 10% odds, just shy of that 0.0928. So that'd be our probability, a little less than 1 out of 10 chance that we don't see our first red light until Wednesday.